Welcome back to Chemistry Chapters, and today we're going to explore one of the most fascinating building blocks of matter, the atom. Everything around us, from the air we breathe to the stars in the universe, is made up of atoms. But what exactly is inside an atom? In this lesson, we'll take a closer look at its three fundamental subatomic particles, protons, neutrons, and electrons, and understand their location, charge, and relative mass in a simple and easy-to-follow way. So let's get started. At the very center of every atom lies the nucleus, a small but incredibly dense core that contains almost all of the atom's mass. The nucleus is home to two important subatomic particles, protons and neutrons. The glowing red spheres in the illustration represent protons, which remain fixed inside the nucleus. Protons carry a positive electrical charge of +1 and have a relative mass of 1 atomic mass unit, or 1 AMU. In fact, the number of protons inside the nucleus determines the identity of an element. Alongside the protons are the neutrons, shown as the gray spheres. As their name suggests, neutrons are electrically neutral, carrying no charge at all. Like protons, they also have a relative mass of 1 AMU. Although they do not contribute to the atom's overall electrical charge, neutrons play a crucial role in adding mass and helping stabilize the nucleus. Surrounding this dense nucleus are the electrons, represented by the bright cyan particles. Unlike protons and neutrons, electrons are not fixed in one place. They move rapidly around the nucleus, forming what scientists call the electron cloud. Each electron carries a negative electrical charge of 1, which balances the positive charge of the protons, making most atoms electrically neutral. Despite their importance, electrons are incredibly lightweight. Their relative mass is only 1/1836 AMU, meaning they are approximately 1,836 times lighter than a proton or neutron. A quick look at the scale illustration perfectly explains the distribution of mass inside an atom. The proton and neutron balance each other on the scale, demonstrating that they have the same relative mass of 1 AMU. Meanwhile, the tiny electron is shown separately with its relative mass of 1/1836 AMU, highlighting just how small its contribution is to the atom's total mass. This comparison clearly shows that almost all of an atom's mass is concentrated inside the nucleus, while electrons contribute very little to its overall weight. To summarize, protons are positively charged particles located in the nucleus with a relative mass of 1 AMU. Neutrons are neutral particles that also reside in the nucleus and have the same relative mass of 1 AMU. Electrons, on the other hand, move around the nucleus in the electron cloud, carry a negative charge, and have an extremely small relative mass of 1/1836 AMU. Understanding these three subatomic particles is the foundation of chemistry. Their arrangement, charges, and masses determine the properties of atoms, the behavior of elements, and ultimately the composition of everything in our universe. At the very center of every atom lies the nucleus, a small but extremely dense region that contains two of the atom's three fundamental subatomic particles, protons and neutrons. The protons, P+, represented by the glowing red spheres, are permanently located within the nucleus. Each proton carries a positive electrical charge of +1 and has a relative mass of 1 atomic mass unit, AMU. Alongside the protons are the neutrons, N0, shown as the gray spheres. As their name suggests, neutrons have no electrical charge, making them neutral particles. Although they do not contribute to the atom's overall charge, they play a vital role in adding mass and stabilizing the nucleus. Like protons, each neutron also has a relative mass of 1 AMU, meaning both particles contribute almost all of the atom's total mass. Surrounding the nucleus is the electron cloud, where electrons, EE, are found. Unlike protons and neutrons, electrons are not fixed in one place. Instead, they move rapidly around the nucleus, creating what scientists refer to as the electron cloud. In the illustration, they are represented by the bright cyan spheres. Each electron carries a negative electrical charge of 1, which balances the positive charge of the protons, making most atoms electrically neutral. Despite their important role in chemical reactions and bonding, Electrons are incredibly light with a relative mass of only 1/1836 mu, making them approximately 1,836 times lighter than either a proton or a neutron. The comparison of particle masses is clearly illustrated by the scale graphic. On the seesaw, a proton and a neutron are perfectly balanced, demonstrating that they have equal relative masses of 1 mu. Beside them, the tiny electron is shown with its relative mass of 1/1836 mu, emphasizing just how insignificant its mass is compared to the other two particles. This visual highlights an important concept in chemistry. Nearly all of an atom's mass is concentrated within its nucleus, while the electrons contribute very little to the atom's overall weight. The atomic number, Z, is one of the most important properties of an atom because it defines the element's identity. At the center of every atom is the nucleus, which contains protons and neutrons. The atomic number is simply the number of protons present in the nucleus. For example, the illustration shows a carbon, C atom containing 6 protons, so its atomic number is 6. This single number determines the element's identity, its position on the periodic table, and in a neutral atom, the number of electrons required to balance the positive charge. Since carbon has 6 protons, a neutral carbon atom also has 6 electrons. The relationship between these properties is illustrated through a simple chain of identity. Everything begins with the number of protons, which directly determines the atomic number. The atomic number then identifies the element and fixes its position in the periodic table. Finally, because atoms are usually electrically neutral, the number of electrons must equal the number of protons. This means that once you know an atom's atomic number, you can immediately identify the element and determine the number of electrons it contains in its neutral state. One of the most fundamental principles of chemistry is that changing the number of protons changes the element itself. Every element has a unique proton count that cannot be shared with another element. For instance, an atom with 1 proton is hydrogen, H. An atom with 6 protons is carbon, C. An atom with 8 protons is oxygen, O. And an atom with 79 protons is gold, Au. Even adding or removing a single proton transforms the atom into an entirely different element with its own unique physical and chemical properties. This is why the atomic number is considered the true identity of every element. A neutron, N0, is one of the 3 fundamental subatomic particles found inside an atom. As shown in the illustration, neutrons have an electrical charge of 0, making them completely neutral. Like protons, they are located inside the nucleus, the dense central region of the atom. Although neutrons carry no electrical charge, they have a relative mass of approximately 1 atomic mass unit, AMU, which is nearly equal to the mass of a proton. Because of this, every additional neutron increases the atom's overall mass. The scale diagram clearly demonstrates this by showing that a proton and a neutron have almost identical masses. Neutrons play 2 essential roles in the structure of an atom. First, they increase the atomic mass by adding weight to the nucleus without affecting its electrical charge. Second, and more importantly, they stabilize the nucleus. Since protons are positively charged, they naturally repel one another due to electrostatic forces. Neutrons help counteract this repulsion by contributing to the strong nuclear force, which holds the protons and neutrons tightly together inside the nucleus. Without enough neutrons, the nucleus would not be able to remain intact. The importance of neutrons becomes even clearer when comparing stable and unstable nuclei. A stable nucleus contains a balanced ratio of protons and neutrons, allowing the strong nuclear force to overcome the repulsion between the positively charged protons. As a result, the atom remains stable and intact. In contrast, an unstable nucleus does not have the proper balance of neutrons. If there are too few or too many neutrons, the nucleus becomes unstable and may undergo radioactive decay, releasing energy and radiation as it attempts to reach a more stable state. This balance between protons and neutrons is therefore essential for the stability of atoms and the existence of many naturally occurring elements. Isotopes are different forms of the same element that have the same number of protons but different numbers of neutrons. Since the number of protons determines an element's identity, all isotopes of an element remain the same element. However, because neutrons contribute to the atom's mass, changing the number of neutrons results in different atomic masses. In other words, isotopes have identical chemical identities, but differ in their mass due to the variation in neutron count. A great example of isotopes is the carbon family. Carbon-12 contains 6 protons and 6 neutrons, making its mass number 12. Carbon-13 also has 6 protons, but it contains 7 neutrons, giving it a mass number of 13. Similarly, carbon-14 still has 6 protons, but it contains 8 neutrons, resulting in a mass number of 14. Although each isotope has a different number of neutrons and a different atomic mass, they are all classified as carbon because they each contain exactly 6 protons. This illustrates one of the most important principles in chemistry. The identity of an element never changes unless the number of protons changes. As long as an atom contains 6 protons, it will always be carbon, regardless of how many neutrons are present in its nucleus. The additional neutrons only affect the atom's mass, and, in some cases, its stability, but they do not alter the element itself. In summary, the relationship between neutrons and isotopes is straightforward. When the number of neutrons changes, the isotope changes. As neutrons are added or removed, the atomic mass changes because each neutron contributes approximately 1 atomic mass unit, AMU. However, since the number of protons remains constant, the element remains the same. This simple relationship explains why elements can exist in multiple isotopic forms while still retaining their unique chemical identity. Electrons, E, are the smallest of the 3 fundamental subatomic particles and play a crucial role in determining an atom's chemical behavior. Unlike protons and neutrons, which are found inside the nucleus, electrons are located outside the nucleus in regions known as electron shells or orbitals. These rapidly moving particles form what is called the electron cloud surrounding the nucleus. Each electron carries a negative electrical charge of 1 and has an extremely small relative mass of approximately 1 to 1836 atomic mass unit, AMU, making it about 1836 times lighter than a proton or a neutron. Although their mass is negligible, their role in the atom is essential. Because electrons occupy the outermost region of the atom, they are the particles that interact with other atoms and determine how substances behave chemically. One of their primary functions is chemical bonding, where atoms share or transfer electrons to form molecules and compounds. Electrons are also responsible for electricity. When electrons move through conductive materials such as copper wires, they create an electric current that powers electrical devices. In addition, chemical reactions occur when electrons are rearranged between atoms, allowing old bonds to break and new bonds to form. Electrons also play a key role in ion formation. When an atom gains or loses 1 or more electrons, it becomes an ion, acquiring a negative or positive charge depending on whether electrons are gained or lost. In summary, the 3 subatomic particles have distinct locations and functions within the atom. Protons, with a +1 charge, and neutrons with no charge are tightly packed inside the nucleus, providing the atom with its identity, mass, and stability. Electrons, carrying a 1 charge, move rapidly around the nucleus in the electron cloud. Because they are located on the outside of the atom and are free to interact with other atoms, electrons determine most of an atom's chemical properties and behavior, making them the driving force behind chemical bonding, electrical conductivity, and virtually all chemical reactions. The understanding of atomic structure has changed significantly over time. One of the earliest successful models was the Bohr model, which described electrons as moving around the nucleus in fixed circular orbits, much like planets revolving around the sun. In this model, the nucleus occupies the center of the atom while electrons travel along well-defined paths at specific energy levels. Although the Bohr model successfully explained several properties of simple atoms and marked a major advancement in atomic theory, later discoveries showed that it could not accurately describe the behavior of electrons in more complex atoms. As scientific research progressed, the quantum mechanical model replaced the Bohr model and became the modern understanding of atomic structure. In this model, electrons do not travel along fixed circular paths. Instead, they exist within an electron cloud, a region surrounding the nucleus where an electron is most likely to be found. Within this cloud are different types of atomic orbitals, including s, p, and d orbitals. The s orbital has a spherical shape, the p orbitals have a dumbbell-like shape, and the d orbitals possess more complex clover-shaped structures. These orbitals are not physical pathways but mathematical regions that represent the highest probability of locating an electron. The greatest difference between the Bohr model and the quantum mechanical model lies in the concept of probability. According to modern quantum mechanics, it is impossible to determine the exact position of an electron at any given moment because electrons move extremely rapidly and exhibit both particle-like and wave-like properties. Instead of predicting an exact path, scientists calculate the probability of finding an electron in a particular region around the nucleus. Areas where the electron is more likely to be found have a higher cloud density, while regions with lower probability have a lower cloud density. This probability-based approach provides a much more accurate description of atomic structure and forms the foundation of modern chemistry and quantum physics.